Okay, students, so we are now in lecture 15, and we have started a little bit about thermometry and barometry. We first approached the problem of thermometry. Now, yesterday we, like in the diagram that I drew yesterday, in the temperature pressure space, if I need to find out the temperature, if I need to find out a particular temperature of equilibrium, I need a reaction which is near vertical. So this reaction can move in PT space, and based on that, we can find out the temperature. Hopefully, if it is absolutely vertical, then it's independent of pressure. And also, you must understand, but at the same time, when you do this for pressure estimates, then of course, you need a reaction, ideally, you need a reaction parallel to the temperature axis, and this reaction would slide up and down based on certain factors, and then we can find the pressure irrespective of the temperature. And the point of intersection gives us the pressure and temperature condition of the equilibrium that we are looking at. This is the important point of thermobarometry. But you know, nothing is ideal, so you don't get really reactions which are absolutely parallel to the pressure axis and absolutely parallel to the temperature axis. What you normally get is there is some amount of angle. So there is some amount of angle. So what happens is, so normally you get a set of reactions which could be, say, temperature and pressure, and this reaction, for example, the one for the temperature, has a steep slope, and one with the pressure has a gentle slope, but it is not independent of temperature, and so that slope is like this. And we get a point. But that's not the end of the story. Because every value that you find, say temperature 500 degrees centigrade, you never get a particular value. You get a value with its error. So you have, normally you say that the temperature is 500 plus minus 50 degrees centigrade. So, around every reaction, there is a zone of uncertainty. Have you understood? There is a zone of uncertainty. And similarly, for the pressure value, there is a zone of uncertainty. So, although you say that your pressure temperature is here, but you have a parallelogram of forces, a parallelogram drawn, defined by the parallel lines of uncertainty. So this is what you get. But you can take another extreme case and you can draw another temperature pressure diagram and take two reactions. One is like this with its error, and one is like this with its error. Now you see what happens. This still is the intersection, is the pressure temperature condition, but now you see the errors coming out of this reaction. This is the error. So what is happening is, although you say that this is the pressure and this is the temperature, but the uncertainty around pressure and temperature are very large. Have you understood? So this, if you do it so large, and if you have another pressure temperature nearby, you will not be able to discriminate. So what one normally does is, why is this large error coming up? Because of the low angle of obliquity, which is theta, the low angle obliquity between the two lines. Here, the angle is much more. Yes? This gives you a smaller error. But if you take low angle intersections of two lines, then you get a larger, much larger error. So normally when you are estimating pressure temperature condition, one should take reactions which have ideally orthogonal slopes, orthogonal angle. They should be divided with 90 degrees, but normally you're not so lucky, you are never so lucky possibly. And so what you do is, you try to take reactions whose PT slopes or the Clausius-Clapeyron slopes are at high angles. So if you have high angle obliquity, your error is small. But if you have very low angle obliquity, then your error is very large. That is why we should always avoid two reactions having very close slopes, Clausius-Clapeyron slopes. You should take two reactions which are at high angles. That is what we should do. And as you know, that ideally it would be, this is absolutely wonderful, because you can put the uncertainty bar here, and you could put the uncertainty bar here, and you will get a pressure temperature value like this. So for doing pressure temperature estimation, or thermobarometry as it's called, you need to have reactions which have steep and gentle slopes. When you have a steep and a gentle slope, it automatically creates a 90-degree oblique angle. A very high angle intersection, which reduces the error on the estimated pressure temperature values. Right? So normally, temperatures have errors of plus minus 50 degrees centigrade. That is the error on temperature generally. Error on temperature is plus minus 50 degrees centigrade. And error on pressure, plus minus, it varies from 500 bars to 1000 bar. 500 bars to 1000 bars. Now, you must imagine this, that these are very large, quite a large value. So what happens, this is the normal error of 50 degrees centigrade for a thermometer. And so your pressure also has an error bar of 500 to 1000. Mostly the error bars are somewhere around 1000 kilobars. 500 bar error values in pressure estimates are sort of rare. More is 1000 bar difference, error on your estimated pressure. So the first thing that we do is study a little bit of geothermometry. But first let us do one thing. We try and understand the basic logic of thermobarometry. What are we doing and what are we trying to do? Now, I will take an equation. It's not important, but I will take an equation. If I write A, B, C, D, then it becomes a little vague for you maybe. So I take a simple equation. Say, for example, I have an assemblage, olivine, orthopyroxene, and quartz. Do you see that? Olivine, orthopyroxene, and quartz. You know by now, it's Mg2SiO4, Fe2SiO4, orthopyroxene is Mg2Si2O6 and Fe2Si2O6, and quartz is SiO2, and this is MgO, FeO, SiO2 system. So here, for example, the degree of freedom C minus P plus 2, system components 3, phases 3 plus 2, degree of freedom 2. Now what happens is, so the degree of freedom is 2. Now once more, what is the independent reactions? How many independent reactions do you have? Independent reaction is number of phase component minus system component. How many phase components are here? 2. How many phase components are here? 2. How many phase components are here? 1. So it's 5 minus system components, which is 3, is equal to 2. Now you know if you add this 2, you should be adding it to 4. So if the Gibbs phase rule says the 2 independent variables have to be added, and this says you have two independent reactions, then you can solve it for the variables, but we should know how many metamorphic variables are there. Now you see, for olivine, an independent metamorphic variable is 1. What is it? XMG olivine or XFE olivine. So for olivine, either XMG or XFE would do. The other one is 1 minus. So the orthoperoxine, it's XMG OPX or XFE OPX. Right? So this is also 1 metamorphic variable would do. Quartz XSiO2 is 1, it's not a variable. And the other thing that are, so how many variables do you have? Metamorphic variables, 1 plus 1 plus 2, this is for pressure temperature condition. And so the number of metamorphic variables are 4. This is exactly the case because 2 plus 2 should be 4. That should be 4 if you can constrain the system. So that has to be 4. Clear cut. Now, what are the input variables that we can give? What are the things that we can give? This can be found out by analysis, as I told you, by analysis of the instrumental machine. This we can find out from an instrumental machine. So these 2 input data are given here. Right? So you are left with 2 independent reactions. And 2 independent reactions, so if you, metamorphic variables, therefore, this is constrained and this is also constrained. So this is constrained here and this is constrained here. You are left with 2 unknowns. 4 minus 2 is equal to 2. You're left with pressure and temperature, and you're left with 2 reactions. So this system can be constrained if you have 2 reactions. Now quickly, once more. So remember, all XMG values are known. What are the reactions? And quickly, Mg2SiO4 plus SiO2 is equal to 2Mg Mg2Si2O6, or you can write Fe2Si4 plus SiO2 is equal to Fe2Si2O6, or you can take 1 and subtract 2 and you get Mg2, so that quartz is taken out. So you get Mg2SiO4 plus Fe2Si2O6 is equal to Fe2SiO4 plus Mg2Si2O6. So that's reaction 3. But out of this, any two are independent. Either this 2, then this is redundant, or this 2, then this is redundant, or this 2, then this is redundant. Any 2 will do. Theoretically, any 2 will do. But I, as a metamorphic petrologist, would take either this combination or this combination. I will either take either 1 and 3, or I will take 2 and 3. I will never take 1 and 2. Although theoretically there is nothing wrong. Theoretically there is nothing wrong. But I will take this because of a simple logic. Remember from my last discussion, lecture 14, this is an exchange reaction. This is an exchange reaction. Reaction 3 is an exchange reaction. And these two are magnesium end member breakdown, phase breakdown reaction, iron end member phase breakdown reaction. So these two are phase breakdown reaction. These two have exchange reactions. This one is an exchange reaction. And I know that if I have to find out the pressure temperature condition from this assemblage, I need a reaction which is dP by dt is equal to infinity and dP by dt is equal to 0. As close you can go to these values. That is what I need. So I will choose the exchange reaction. I will tell you why. Remember, for a reaction for dP by dt is equal to infinity, this is delta SR of the reaction by delta VR of the reaction. This infinity can be done if delta VR tends to 0. If delta VR tends to 0, then dP by dt should tend to infinity. This theory I know. Now I will take 3. Why? I will tell you why. For this reaction, delta VR is product minus the reactant. So volume of Fe olivine plus volume of Mg in OPX, this is the product as written, plus V Mg olivine plus V Fe OPX. Right? Now you see here, this can be written as V Fe olivine minus V Mg olivine minus V Fe OPX minus V Mg OPX. And now you know that the ionic radius of Mg is 0.66 angstroms and Fe is 0.74 angstroms unit. So you can well imagine that if I take iron minus magnesium, this will have a slightly higher volume than this, right? If so, then you will have a small positive value. A small positive value for the products because it's, for this bracket, because it's iron minus magnesium. Iron is the one with the higher ionic radius. So you will have this volume minus this volume would be a small positive volume. And again, if you go here, this will be a small positive volume. But then this small positive and this small positive, they are separated by a negative sign. So your delta V essential is a very small value. Have you understood? So your delta V of the reaction is a very small value. So there you go, delta VR tends to 0 for an exchange reaction, any exchange reaction. Delta VR tends to 0. If delta VR tends to 0, then dP by dt should tend towards infinity. So I have got a reaction which may be very close, parallel to the pressure axis. That is why I will take this one. But if I go to the other one, it's a phase breakdown reaction. And there I will never get del VR tending to 0. I will never get it. It's impossible. It will have a value which is much more than what you get from an exchange reaction. So that reactions, these reactions will have some amount of slopes. But this one, delta VR, would be absolutely vertical. That is why I will take 3. If I take 3, then the choice is you can take 2 or 1, depends on you. And the intersection of that will give you the values. So for our case, then remember all exchange reactions have delta VR as very small. So slopes of all exchange reactions are nearly parallel to the pressure axis, or at least dP by dt slope is very high for all exchange reactions. Or sometimes they are very close to 0, which would make dP by dt infinity. You don't need a pressure input to estimate your temperature. You don't need it. But if it has some slope, then of course you need it. You need an input data for pressure. Okay, so let's say I take this reaction, these two reactions. You see here, Gibbs phase rule says any two would do. So 1 and 2 should have technically done. But I told you what happens. You can understand the slopes of the two reactions would be similar or close. I don't want it. So I take the Gibbs rule but make it convenient for me. So it becomes user-friendly. But ideally it should not work because according to this thermodynamics, it does not take into account errors. It does not take into account errors. But this is by my choice. So now, I will just rewrite these two equations once again. 2 and 3, right? So what was 2? Fe2 SiO4 plus SiO2 is equal to Fe2 Si2O6. This was our reaction 2. And the other reaction, I don't know what I wrote. Okay, it doesn't matter. Fe2 SiO4 plus Mg2 Si2O6 is equal to Mg2 SiO4 plus Fe2 Si2O6. And this is reaction 3. Now, let us write the thermodynamic equation of state for reaction. For any phase, once again I'm writing it, G is equal to H0 minus PS0 plus PV0 plus RT-ln activity. This was the equation we chose. This one essentially is G0. Remember, in doing so, we have made certain approximations. What are the approximations we did? I will recollect it from that class. All the heat capacity terms were neglected. All the heat capacity terms were neglected. And the thermal expansion and the isothermal compressibility data, which accounts for the change in volume as a function of pressure and temperature, that was neglected because we took volume as independent of pressure temperature effect. So we were taking minerals as absolutely incompressible material. So thermal expansion data, volume expansion data, it all does not matter. So these are the approximations involved in that reaction, in writing this reaction. So there will be, if I try to write this reaction, and this was, I don't know, remember some lecture before. So for reaction 2, I will have 0 is equal to del H 0 R2 minus T del S 0 R2 plus P delta V0 R2 plus RT ln. Now what? Now I write this term, please tell me whether you understand it. Activity of Fe2Si2O6 in OPX divided by activity of Fe2SiO4 in olivine into activity of SiO2 in quartz. Since quartz is present, this is equal to 2. This is for reaction 2. This is for reaction 2. Del H0 R2 is enthalpies of the product minus the enthalpies of the reactant. Entropy, similar. Volume, I wrote one before just now for another reaction. Plus RTLN. Now you will see what will you have for the activity term. If I did write every term, there will be one equation of state 2, equation of state 3 expansion, and then I had to subtract it. Then I would have written RT ln activity of Fe2Si2O6 in orthopyroxene minus RT ln activity of Fe2SiO4 in olivine plus RT ln activity of SiO2 in quartz. This is what I would have written. Product minus reactant. So this one, if I take RT out, then I get this expression. If I take RT out, then I get this expression. And here, since I have quartz, activity of SiO2 is equal to 1, so this is just a ratio of this. Right? So, that is for reaction 1. Now you see here. This is important. What do we don't know here? What do we don't know? You see, this is temperature we don't know. We don't know the pressure. All other thermodynamic parameters are known thermodynamically. And you have to find out activity of Fe2Si2O6 and activity of Fe2SiO4. You know that they can be written in terms of, okay, we will check up. This is unknown, and I will just write this one and this one for you at the moment is unknown. Right? Now, I have given the derivation in the PDF 2 where I talked about activities of crystalline solution, where I have shown that in a binary solid solution, RT ln gamma A is equal to WAB into XB squared. And RT ln gamma B is equal to WAB into XA squared. I have derived this. So if I do this, assume therefore, if I take this and do it for this one, then what will I get? You see what I do. RT ln activity of Fe2Si2O6 in orthopyroxene is equal to WFE mg orthopyroxene into XFE squared. Remember, you know WFE mg value. These are all thermodynamic parameters that need to be known. Gibbs phase rule does not care whether WFEMG you could find or you did not find. It will consider as your found. Right? And similarly like this, I would find RTLN activity of Fe2SiO4. Now this one, SiO4 in olivine is equal to WFEMG olivine, this is known, into XFE in olivine whole squared. This is what you will have. Fe olivine whole squared. There is a little more complication that I will do in the next class. I will not get time in this class to do it. I think if we can... So this is how it works. RTLN gamma A is equal to WAB into XB squared. If I transfer this to the orthoperoxide, where RTLN activity Fe2S, you see here, if this is A, this has to be B squared. Right? So if I take... RTLN. You see, I made a mistake. See, I made a mistake. So if this is RTLN gamma A, if A is Fe, then this should be Mg. And similarly here, if this is AB, this has to be Mg. So if I do this now, and if I incorporate this expression into this, what will I get? Zero is equal to, now what I will get, del H0 R2 minus T del S0 R2 plus P delta V0 R2 plus RTLN. Now you see what I'm writing. Okay, I think, no, I'm sorry here, I just made a mistake. Sorry. Hang on. Please correct this. Gamma olivine. This is not activity olivine. It is RTL and gamma olivine, excess mixing. RTL and gamma FeSi orthoperoxide, and this is gamma RT itself. So now you will have an RTLN term. Okay, let me do this. Activity of Fe2SiO4. You see, mixing is on two sides, is equal to XFE olivine into gamma Fe olivine into whole square. Have you understood? Activity Fe2SiO4 is equal to Fe activity XFE into olivine, gamma Fe into olivine, and the whole into squared. That is very important. It's all very squared. So what will happen here, you will have, if you take now RTLN activity Fe2SiO4 in olivine, therefore you will get RTLN XFE in olivine into gamma Fe in olivine whole squared is equal to 2RTLN XFE olivine plus 2RTLN gamma Fe olivine. And this can be written as 2RTLN XFE olivine plus 2 into WFEMG XMG olivine, or XMG, not XMG olivine, it is 1 minus XFE olivine whole square. You see, it should have been XMG squared olivine squared. XMG olivine is 1 minus XFE olivine. Why? Because I wanted to keep the consistency here. Have you understood? So what we will have is, once again, if I tell you, look at you correctly, activity of Fe2SiO4, that means iron magnesium mixing on two sites. And those two sites I have not distinguished here. SiO4, then at every site, XFE into gamma whole square, the subscript is raised to the power. The subscript is raised to the power. That's the cardinal rule. The subscript is raised to the power. Now if you do this, then RTLNA activity of FeSiO4 will be RTLNX into this. Obviously, this is what it is. So now you will have, if you break it up, 2 will come here, 2 RTLNX Fe olivine plus 2 RTLN gamma Fe olivine. Right? If you break it up further, this would be the same, is the same. And here, instead of 2 RTLN gamma Fe olivine, you will have 2 WFEMG. This 2 is nothing but this 2. And this will be 1 minus XFE olivine whole square. This is what it will be. So, for this equation or for this reaction, if we blow it up, then we will have I am doing it together, you please check it. This is what it will be. This expression. This is the expression. I'll give you 2 minutes to think it over. Remember here, this I have not written olivine here. So this should come in here as olivine. So here, this term here, XFEOPX by XFE olivine, there will be one term like this in olivine. That is what I said. When I derive something and when you read it, just don't read it like this. Put in your pen on your paper and then you derive it. It is possible that while I'm deriving, I might have missed a sign. But you should be able to correct it. There is nothing to mug up here. Right? So, because it's Fe2SI2O and here, so I will have a term which will only involve XFEOPX by XFE olivine. This term you see is ideal mixing, energy term due to ideal mixing. There is no gamma term there. The non-ideal part of it is included here. Non-ideal part. This is the product. Orthoperoxine, FEMG, 1 minus XFEOPX whole square. This is the reactant. Of course, quartz does not matter because quartz is pure. So this does not appear in the mole fraction, does not appear in the W values. So this is exactly what it happens. So I'll give you 2 minutes to think about it. So this is the equation that emanates from reaction 2. This is the equation that emanates from reaction 2, where you have this as the equation. This is for pure end-member components. That means if these were all pure, then this will be the part. This would be the part if everything is pure. If everything is pure, this would be the part. If it is only ideal, this would be the part. And the non-ideality is this part. So this is how it goes. For this reaction, this is the pure phase component contribution to energy. This is the ideal mixing contribution to energy. And this is the non-ideal or excess mixing contribution to the energy cycle. So that is all what you have in this system. Right. Now let us look at this expression a little bit more. It's a very simple way of writing it. If I took an asymmetric solution, you would have 4 W terms. So it's more complex. But anyway, this is the pure phase contribution to the energy, ideal mixing contribution to the energy, and this is the excess free energy mixing contribution to the energy. Right. Now, what do we know? Which ones do we know? That first we will talk about. What terms do we know? We know del H0. We know del S0. We know del V0. These are thermodynamic terms. We know R. We know W, FeMg orthoperoxine. We know WFeMg olivine. So these terms are known. What are the unknowns? What are the unknowns? Temperature, pressure, temperature again. And you can see XFeOPX, XFeolivine. The same XFeOPX comes here. The same XFeolivine goes here. Do you see that? So there are 4 variables. There are 4 variables in this expression. Pressure, temperature, XFeorthoperoxine, XFeolivine. Remember our variables, metamorphic variables? Now, but these 2, XFeOPX and XFeolivine, these 2 variables we can find from the instrument. These 2 we can find from the instrument. Mole fraction, if we can analyze the orthoperoxine and the olivine, we will get these 2 values. So if we get these 2 values, it boils down to unknowns in pressure and temperature. It boils down to unknowns in pressure and temperature. So this equation, if the compositions of orthoperoxine and olivine are unknown, then it has 4 values. But once we analyze this orthoperoxine and olivine and find out XFE, the number of variables are 2. So we have taken reaction 2. What will be the equation for number 3? Now what I will do is, I will write down the expression. You will derive it. But just before we do it here, in this term, I will give you the clue. You will write down what will be the expression. Now, how will the equation look like? There's very little space here, so it's difficult to write. I'm writing with this one here. So this is reaction 3 now, right? This is reaction 3 now that we are talking about. So reaction 3, if I write, then 0 is equal to del H0, but now R3, not R2. These are different values. Minus T del S0 R3 plus P delta V0 R3 plus RT ln product minus reactant. So here you have activity of Mg in olivine into activity of Fe in OPX divided by activity of Fe in olivine into activity of product Fe. Activity of Mg in OPX. This is what will happen. This is what is written as. This can be changed a bit and you can write delta H0 R3 minus T delta S0 R3 plus P delta V0 R3. Remember, this value would be very small for the exchange reaction. Plus RT ln. Now, activity of Mg by activity of Fe in olivine divided by activity of Mg by activity of Fe in orthopyroxene. I have done nothing. Activity of Mg by activity of Fe in olivine is correct. And then I divided it, so this should be reversed. So activity of Mg by activity of Fe OPX. Have you understood? So what will you have from here is 0 is equal to del H0 R3 minus T del S0 R3 plus P into delta V0 R3 plus RT ln activity of Mg by activity of Fe in olivine minus RT ln activity of Mg by activity of Fe in OPX. Do you see that? I have split it up into two. I will do one of this. I just have a little bit of time and I will do this. You derive it later. So now, here I will derive this one. Look at here. RT ln activity of Mg. This will be, this one here, will be activity of Mg in olivine minus RT ln activity of Fe in olivine. Yes or no? So this will be equal to RT ln X to RT. Why it's Mg? Because Mg is mixing on two sides. Mg and Fe are mixing on two sides. So RT ln XMG olivine plus 2RT ln gamma Mg olivine. This is one term. Minus 2RT ln XFE olivine plus 2RT ln gamma Fe olivine. Right? Right? I think I will erase this part. If I do this, then from here I can write 2RT ln XMG by XFE olivine. This term is gone. This term and this term is gone. This term and this term are taken into this term. Plus RT ln gamma Mg olivine. What does this mean? W FeMg olivine into, this is Mg, no? So this will be XFE olivine whole squared minus same WFeMg olivine into XMg olivine whole squared. Whole squared. So if you do this, then it will be 2RT ln XMG by XFE olivine plus WFeMG olivine into XFE olivine squared minus XMG olivine squared. Yes or no? Now you see, this term here is a square minus b square, which is a minus b into a plus b. But a plus b equal to 1. Isn't it? A plus b is equal to 1 because XFE olivine plus XMG olivine is equal to 1. So this will be, essentially this will be 2RT ln XMG by XFE olivine plus WFeMG into XFE olivine minus XMG olivine. That's all what you get. This is for the olivine term. Remember, this is this term. This is this term here. This term can be written as we go from here, as we go, and we can write it till here. So this is the expression that you get. I think I will stop here now. So you can do the rest of the thing, derive, and we will continue in the next class. In the meantime, 9th, you have an examination, February, the day after tomorrow. So I will also send you a message in the classroom.